later on if you're using the videos. Okay, go ahead. When you're doing, so which part you're looking at?
Your E-questions?
Yeah, go ahead.
So with the PSSC, I understand
Uh-huh.
how to do the equation, but
Okay.
when I would do it for like E2 or E3,
Sure.
and then check the answer, I was so...
No. Careful. Remember that I approximate maybe a little bit off of what you guys approximate. So we'll run E2 here to show you what I'm talking about. But first of all, let's back up. Great question, Tabitha. Let's back up though. Look at PSSC. The reason I included this problem in here is I asked a couple questions in class a few days ago. If you have data that's shaped like this, how would you describe it? How would you describe it? Would you describe it as bell-shaped? Would you describe it as not bell-shaped? And then there's differences in the responses. Some people say, oh, it's symmetric, it's bell-shaped, it's unimodal. Some people say, oh, it's skewed a little bit. And here's the news. Every data set is skewed a little bit. Every data set. No data set exhibits perfectly bell-shaped behavior. If it does, something's wrong with it. There's always going to be variation in it. So when you look at this guy right here, this E2, you look at this. Would you guys call that a bell-shaped distribution?
Yeah.
You would, exactly. But it gets tricky. It's like, how close is it to a perfect bell? That's what that PSSC computation does. It gives you a quantifiable measure to measure the skew based on a certain set of characteristics. So the first thing we got to do is we got to calculate, in order to use that bad boy, we got to calculate the sample average, the sample median, and the sample standard deviation, and we put all that stuff together on the PSSC. So I say let's do that right now. Let's do that first. This is a great exam review question, by the way. Not the PSSC, don't vomit. Getting those numbers from this graph. Getting those values from this graph is a great exam review question. So let's do that. Let's do that. How could we get the sample average, the sample standard deviation, the sample median, everything, even the mode, although the mode is not necessary for this calculation. How do we get all of that from this graph? I'll give you a hint. Picking this up. We're going to use technology for sure. I mean, unless you don't want to. I think we do want to, though.
Yes, technology.
Yes, I think we like technology. The reason we invented computers in the first place was to do math for us very quickly. I know it's hard to believe, but it's not to do Facebook. What's the verb? It's not do Facebook. Is Facebook a verb? Like to Facebook?
To Facebook.
He Facebooks, she Facebooks,
Yeah.
it Facebooks. Facebook is a verb.
I think it's a verb.
Because like Twitter is tweet. I didn't know if Facebook was something like, I don't know. I'm at a loss right there. I'm at a loss. Hey, look at that. Yay. So, help me out, friends. I want to get the average. Where do you think the average is, ish?
Around 5.
Yeah, I think so too. It's the highest part of the bell. About the median, ish 5, right? Ish 5. Where would the mode be? The TI will not give you the mode. Where would the mode be? Exactly. How are you pulling the mode off of this? That's the mostest. That's right. I love this class. It's the mostest. From Colin back there. Yes. it's the mostest. The highest bar. The highest bar. Good. And the median and the mean will both be gotten for us via the computation. Standard deviation. That's the one that there's really no. There's tricks to approximate where the standard deviation is. Since this is bell-shaped. Actually, you know what? Let's give it a whirl. Let's give it a whirl. Since this is roughly bell-shaped data. Tell me about that empirical rule which we spoke of in class last time. Remember that cool empirical rule? Nice. You got 68%, you got the 95%. So let's use the 95. That might be the easiest one to use. So we said 2 standard deviations. Perfect. Somebody just said it. Kelsey, thank you. So here's average. According to that bell-shaped empirical rule, we should have about 95% of the data within 2 standard deviations of that average. So what I'm going to do is I'm going to start here, and I'm going to blow out this way. You guys stop me when you think I've gobbled up about 95% of the data. About here-ish? Okay. So looks like we went from about 3.75 to about 6.25. Let's write that down. This is just to kind of see how close our ishing comes to what scientifically and mathematically comes up as a standard deviation. So here's the ish computation of S. And the reason I'm doing this is because if you need to get this value and you don't have technology readily available, this might be a cool way of actually getting a close value or a close equality of what S is. So we just said that 95% of the data is roughly between 3.75 and 6.25. And we went to the outside. I think you guys went to the outsides of those bars. So it wasn't like you stopped halfway. You kind of went to the outside. All right. How far are those apart from each other, friends? Is it 2.5 apart? 2.5 units apart?
Yeah.
Okay. So basically, it's 2.5. This is LDL, so it's whatever the unit is. I think it's milligrams per deciliter. Tammy, you agreed with that a couple weeks ago. So it's about 2.5 milligrams per deciliter from here to here. Here's a fun question. Remember how the standard deviation is that S value that the TI kicks out, but a number of standard deviations is plus or minus that S value from average. How many S's make up this range of values?
2.
How many? I heard 4, I heard 2,
6.
I heard 6. Do I hear an 8?
You can go as many times as you want.
But how many make up 2 standard deviations?
Oh, 4.
4, right? It's gotta be 4. Because think about why. One standard deviation starts at the average and adds and subtracts 1 to get the entire range. So within one standard deviation, there are 2 S's. To go out one more standard deviation, you have to tag an S here and tag an S here. So there's 4 total S's. You guys buying that logic?
Yeah.
There's 4 total of that S. I want to throw out my apology here too for all statisticians. The fact that we're talking about the sample standard deviation. I should put the camera over here so you can see what I'm pointing at. The fact that we're talking about the sample standard deviation and then a number of standard deviations is somewhat confusing because you're hearing the same phrase and it means 2 related but slightly different things. So are we cool with Tabitha? She said there's 4 S's within 2 standard deviations. Solid? Okay, so let's get a ballpark. If this is 2.5 wide and 4 S's make up that 2.5 units of difference, 0.675, did that math right?
625.
0.625, dang, I didn't do the math right. S should be ish 5/8 of a milligram per deciliter ish, somewhere in that neighborhood. It's all ish, we're ishing this. Let's see how close our ish comes to the actual mathematical computation that the TI does. Does that logic make sense though, as far as like dropping your hands out till you're trapped? It's only going to work consistently with bell-shaped data. But I figured, what the hell, it's bell-shaped. Let's give it a whirl and see if we can get close. Cool? Fair? I didn't have it, that wasn't part of the homework question, but what the hell, let's explore. Since you're going to see bell shapes a lot in this class, and outside of this class. Mood lighting, very nice. Do you guys like it better up, lights on or off? On?
Yeah. It's less straining.
Is let's start with them off or
No,
on?
It's less straining with them on.
With them on, gotcha. Okay, so let's go to the TI now. Let's swing this back around so we get a nice visual on how to put the data in. So we're going to be up here. Let's make sure we can see this. Good. We get an average result? Yeah. Find a mode. Now to the yes or no, or abstain. So how do I get the data in, friends? I've turned the TI on. I'm studying for my exam. I tell you on the phone. What do I do? Stat. Edit. I got crap in here. Clear it. Press delete, right?
No.
Good. Press clear. No. Trigger response. Don't. What goes in?
Well, we have to take the average of the bottom set of data points.
Excellent. When you have group, like I said, this is a perfect exam review question because I like giving you guys grouped data to play with. Your quiz from last week had that in there. Your quiz that's due Wednesday has group data. You're going to have at least one of those on the exam because it happens. It's how data comes to you in the world. It's worth looking at over and over and over again. So between 3 and 2, oh, actually we can leave that one off because there's nothing there. 3.75 to 4.25. We're going to call that 4. FYI, if you want to put this one in 2, it's totally fine. It won't change your answer because you'll put a 0 in for frequency. It doesn't matter if you do or don't. We'll just jump right to 4. How about this one? And I think you guys know what's going on now. 5.5, 6, 6.5. There we go. Solid, all the way up. Is anybody disturbed that 6.25 is here and here? Totally cool if you are, by the way. Anybody disturbed by that? If you're not disturbed by that, tell me why you're not disturbed.
Because it's only like between 5.75 up to 6, not but not including.
Nice,
6.25.
nice, Tabitha. Awesome, awesome. What kind of data is this? By terms by type, qualitative, quantitative. We know it's quantitative. Discrete or continuous. The unit is milligrams per deciliter.
Continuous.
Totally continuous. Milligrams, deciliters. That's a measure of weight and a measure of volume, both of which are measured. So there is no such thing as exactly 6.25. As Tabitha correctly pointed out, it's up to, rounded to, if you will, up to 6.25, and this is rounded to down to 6.25. But that you'll never actually hit exactly 6. It's like saying I'm exactly 5'11 and a half. No, I'm not. Depends on what time of day, depends on how straight I'm standing, how much my hair is sticking up. It varies within. I round off to 5'11 and a half. So, good, good. All right, now here, going back, Tabitha, was it you were the one that asked the question about this, right, about the PSSC. Here's where the differences can occur, honestly, is in what you pull these frequencies for. So what are you going to call? How many of those, that 4 do we even think that is?
7.
I think so. How about the next one?
26.
I'll buy that. 32? 22? Okay. 5? 4? I'm down with that. This is one place where the differences can occur. If folks, and especially on that house one, where they're hundreds and not just tens, that can create a whole other issue too. So again, don't sweat too much on that. Don't sweat too much on that, because if your answer is not jiving with mine, I know that. There's tons of gray in this class, and I understand that when I'm grading. Also, put your mind at ease. Just take a pause here. Put your mind at ease. The data sets that I've used for your in-class exams are extraordinarily neat and clean. So everybody will be getting the same averages, the same standard deviation. I don't like freaking you guys out with gray, a lot of gray in the in-class parts. It just doesn't make sense. It puts you through, like, it makes you all agita written. And I just thought, I don't want to do agita. Got any Italians in here? Agita? No Italians. That's right, I've been. Agita. Agita is like angst. It's like Italian angst. So imagine a little 4-foot tall woman. Hey, you giving me agita? No Italians. My grandma. Sorry. So cool. Data's in. Let's get the measures we need. We need an average. We need a median, and we need a standard deviation. So how do we do that? Stat. Calc. Very nice. Always 1 bar stats, because there's one variable, the LDL level. Press enter, right? Nice. If you press enter right now, you will get an answer, and it probably won't be the right one. I mean, it'll gladly give you numbers, but the problem is it's not looking at the actual frequencies that are included. So you have to not just tell it that. Just like Cassie said, we got to tell it L1, L2. Which now has it look at the actual frequency counts in L2 for the data on L1. It's cool? Cool enough-ish? Okay, good. There we go. There we go. So we got an average reading. You guys were damn close. I mean, you said 5. That's 5, essentially. We got a sample standard deviation about 0.59. That's not too far off what we approximated, which is pretty slick, actually. And it's cool. And then the median, where's the median? I see 2 things. I see the average and I see the standard deviation. Where's the median? He's down. He's down, Aaron. You got it. He's down here. And there he is right there. He's 5. Whoops. There he is. He's 5. Go ahead. Go ahead, Francesca.
So I guess I'm not understanding, because looking at the data and then comparing it to what comes up on the TI.
Yes.
If I look at that data, I would say the median is 5.25. If I look at the graph.
What are you looking at 5.25 here or here?
I'm looking at those two would be the median calculation.
Ah, I see what you're saying. So you're saying they're both in the middle.
Yeah.
So did you actually go through and chop?
Yeah.
You did.
Well, I chopped, and then I also took 3.75 and 6.75, and the center of that is 5.25, directly in the middle.
So let's just real quick, let's do exactly what you're saying, Francesca, because it could be, there are different, we're in statistics right now, not the probability part of the course, but the statistics part, and I've never analyzed the TI's computation of a median before, but there are certain computations of medians that allow for the height of the bar and where you land after chopping. So in other words, we've chopped in class before, chop, 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 chop. And once we're within a bar like this, we just call it 5. But some computations, and I don't know if the TIs, like we'll find out here in a second, if you end up chopping and you're up here at the top of the bar, they'll count you closer to this side. or closer to this side if you're at the lower end of the bar. So basically it's positioned within the bar. Let's find out. Let's just do a real quick old school chop. So I got 7 here, right? Chop those 7 off. Chop these 4 plus 2 more. Plus 3 more, excuse me, plus 3 more. So now they're gone, and most of this is gone. I got 2 here, right? Yep. So chop those 2 with those 2. Now I'm here, here, and here. Everything's here. So let's just chop all of these, and then chop all of these, but now I have to borrow 3 more, don't I?
3, yeah.
So I borrow 3 from this one. Now everything left is in this bar. So therefore the TI is using the median like we do. Since everything left is in this bar, the middle will be in that bar, which we'll call 5. Does that make sense?
Kind of, yeah.
But you see, the idea is once you symmetrically chop, once you've chopped off the highs and the lows, you end up exclusively in this bar. So therefore, you can stop chopping at that point because everything left is in the bar, and everything in the bar we're calling 5-ish. Is that fair-ish?
So, and that's only with when you have a range, right? If you have actual data points, then
You do it the same way, yes, and then all of them wouldn't be 5. There'd be some variance from 4.75 to 5.25. You'd have 4.8s, 4.81s, 4.92s, 5.13s, and then and I doubt very much you'll come up to exactly 5, but I bet it'd be close to 5. Fair? Great question, by the way, fantastic question. But, so it looks like the TI is crunching a median the same way we do, and it's not allowing for the up and down in the bar. I've never liked that because there's an assumption that you know something about the data. See, here's the deal. When you do that, well, I shouldn't really say that. So if you end up when you're chopping closer to the top and you take a higher value, I don't know if I like that or not. Don't worry about it. Let the T. I mean, there's arguments for and against it. So just don't worry about it. Let the TI do the sorting for you. Cool? So now we have everything we need. We've got the median, we've got the average, we've got the sample standard deviation. All we've got to do is crunch that PSSC, which is mean minus median, divided by the sample standard deviation. Okay? Now, something, do you want to see the shortcut, the variable shortcut on the TI, or do you want to just plug the numbers in?
That was really confusing. On the homework or on the quiz when you're like, type this.
So I think that's a big fat no. Let's not do it that way. Let's just run the numbers. Good. Yeah, on the quiz for this week, thank you, Tabitha, for bringing that up. I give you some shortcut button pushes for how to pull, like, for example, instead of having to type, whoops. There we go. Instead of having to type 5.0154 blah, 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 you can just type the X bar symbol in. Let's not do that. Let's just call it 5.02. Yeah. So, we're going to go, to get that PSSC, 5.02, that's the average, minus the median of 5. And I'm arbitrarily cutting the mean off at 2 decimals. Really doesn't make a whole lot of sense to do that, but I'll take a couple decimals. And we're going to divide that by the sample standard deviation, which looks like 0.588. So all I'm doing is I'm using that Pearson's formula that was in your homework.
Are we going to have to memorize?
No! God, no! There's no memorization in this class.
Okay.
No memorization. Anytime
Oh,
brings up another point. If you ever think you need a formula on an exam, just ask me. I'll write it on the board. Like I want to calculate the sample standard deviation by hand, Sean. I'll look at you kind of funny, like why? And you'd be like, because I want to. Okay, here it is. I'll put it on the board so everybody has it. But I don't want you filling your head with memorization and definitions. I want you to applications, all that application in here. No memorization, Raphael. Boom, there it is. There's your Pearson's. Now, what you do with it, this is the part that's a little bit, that is open to discussion. That gives you an idea of skew. It's positive. Since it's positive, that means the average is larger than the median. Do you see why? The average, mathematically, why the average is not much larger, but a little larger than the median?
Yeah.
Because it's positive, and since you're going average minus median, if it's a positive, this is always positive. The sample standard deviation is always positive, or it can never be negative, I should say. So if the whole thing is positive, that means the numerator was positive, which means the average was bigger than the median. And all that means is there's a little more data on this side than there is on this side. Remember, who does the average chase?
Tail.
Average chases the tail. If the average is a little bit higher than the median, that means the tail on the right side must be pulling a little harder than the tail on the left side. But, go ahead, Raphael.
Can you repeat that one more time?
No, absolutely. It's a great thing to say. The average is sensitive to outliers. The median is not. So, it's a bell shape. We agree with that. But it's not perfect bell shape. It's bell-ish. Since it's a positive PSSC, or Pearson skew computation, that means the average is pulling a little bit further right than the median is. And the reason the average is pulling a little bit further right is because there's a little bit more data out here on the right. But the question is it so much pulled to the right that we're concerned about calling this a bell curve? That question has more than one answer. But that's why I quoted that one researcher in your paper there. Hildebrand, right here. And this is in 86, and nobody's touched it up since 86, so I'm guessing it's still used in journals and whatnot. Any absolute value of PSSC greater than 0.2 shows skewness enough to be careful about calling something a bell shape. Is our PSSC's absolute value bigger than 0.2? No, it's about an order of magnitude less than that. It's 0.03. It's not even 0.02, it's 0.03. So this is not big enough for us to concern ourselves with great skewness, which means there's no reason to think it's not bell-shaped. That's Hildebrand. Is that fair? It's a lot of words, but basically, what the PSSC does is it sets up limits, 0.3 and negative 0.3. And it says, as long as your PSSC falls between those two numbers, you can call whatever data you're looking at bell-shaped. That's all it's saying. That's all it's saying. Fairish. Fairish. Now, I show you in a couple questions later why you can get a number that's within that range that still doesn't look bell-shaped. So the reason I bring that up, and I explain it later in the homework, is you can't blindly follow a number. You have to look at the entire data set. But if something, basically, what I like to think of a PSSC is, a lot of time in statistics you have these things I like to call second-pass filters. So you've looked at it. You say, I think that's bell-shaped. So you run the PSSC, and that says, okay, that's the second thing telling me I think it's bell-shaped. Is that fair? I call it a second-pass filter because it requires you as a human being to look at the data and say, okay, it looks kind of bell. Here's the problem. When you go down and look at E4, remember these guys? Remember these guys from before? It's the same data set. The PSSC for that data set is almost exactly 0. Now, almost exactly 0 means that there should be no skew. But this data set is essentially all skew. It's bimodal. And the reason it's essentially all skew is because the average and the median are so close together because the skew, if you will, balances out and tracks back to the middle here. So when you actually run the PSSC blindly without looking at the data, it comes up at like whatever it is, negative point blah blah. And it looks like, oh, there's no skew. But you wouldn't have even gotten to that point. You never would have calculated a PSSC for this if you were doing this in your job, because you would never think that was bell-shaped, would you? How many of you would look at that and go, oh yeah, it's bell curve, got it, done, lunch? No, you wouldn't do that. You look at that and go, holy crap, it's bimodal. Hold the presses, we don't want the average. I'm not gonna run a t-test, that's the hell with that, I'm gonna do something else. So that's why I don't want memorizing formulas. Memorizing formulas doesn't teach you how to use them. It just teaches you how to plug numbers in. You have to kind of learn about it in context, which becomes wordy. I know that. It becomes wordy. It becomes looking at all these blocks of text and blocks of graphical descriptive data. But you're going to be doing that in your jobs anyway. So why not start learning it now? Ish? Makes sense? So Tabitha, don't worry if you're not getting the same numbers as me. I'm not concerned about that. You shouldn't be either. You shouldn't be either. There's so many different places. If you rounded differently than me, you might get a different result. So what I'd be concerned about is if you ran that problem we just did and your skew coefficient was 8.76 or something like that. Then I'd be concerned that something was going on. Did you catch this? When I ran that calculation, the parentheses there, you guys caught that, right? That makes a huge difference if you don't do the parentheses versus doing the parentheses. And you remember this in your algebra classes. So that's another potential place things can go wrong. So no, do not memorize formulas. As a matter of fact, on your take-home exam, there's an Excel command that calculates that for you, and I give you an extra credit point to go track it down. So that's what I want. I want you to not memorize formulas, but to know what the result of the formula actually means. That's what I really care about. That's what you should care about too. But I know you're not trained that way. You're trained to other math classes where everything's memorized. Not here, not here, not here, not here. Please, this is Dave. This is Dave?
Yep.
This is Dave, yes. Said your name 5 times.
So TI-84, do the L1, L2?
Yes. Oh, can I fix this? I can fix this. Well, you can leave it like this too. just put L1 there and freak list is L2.
Oh, okay,
Just
gotcha.
so they get used to
So I
that,
need
that's
a
fine.
comma, all right.
No, don't need a comma. You don't, because it's a stat mode turned on to 84s.
And make sure alpha's off.
And alpha's off, yes sir. Is anybody else with an 84 when they try to run one of our stats getting a strange screen that says, is it X list and freak list, Dave, on yours? Is that what it says?
Yeah.
X list and, or just list and freak list? Okay, everyone else is gonna look like this one then. Kelsey.
If our calculator does something weird during the exam.
Just come see me. Yes, please. If something happens during the exam with your TI, bring it to me. Don't sit there for half an hour and try to fix it on your own. Let's just fix it. Yeah. I don't want to, because all that does is create angst. Agita. You start using this word, it's a wonderful word. Agita. Giving me agita. And it blocks your brain out from doing anything rational. Let's fix it. We'll fix it for sure. Cool? Good. That's a great practice problem, actually, just to pull those statistics off. Not even to use the PSC, but just to pull those from the data, which is great. What else? Anything else from in here give you guys grief? Please, Jess.
The lights went dark again.
Oh, they did, son of a...
They slow play you.
Yeah, they do.
They slow play me.
Yeah, like you don't
Slowly
notice
go
it.
on.
'cause
Oh,
they're
yeah, somebody said that they're on a motion detector.
Yeah.
And I said, I don't...
They are, but